Welcome to this rigorous scientific lecture on one of cooking's most fascinating physical phenomena, why pasta transitions from al dente to mushy in what seems like an instant. Today we'll explore the material science, thermodynamics, and structural mechanics behind this culinary transformation. Let's start with our central question. What physical processes cause pasta to transition so rapidly from firm and elastic to soft and mushy? The answer lies in understanding pasta as a composite material undergoing hydration-induced structural changes. Dry pasta is primarily composed of starch and gluten proteins. Starch makes up about 70 to 80% of the mass, while gluten proteins constitute 10 to 15%. Water content in dry pasta is typically below 12%. Think of dry pasta as a rigid composite material. Starch granules, shown here as circles, are embedded in a continuous gluten protein network. The starch exists in tightly packed crystalline and amorphous regions held together by hydrogen bonds. At room temperature with low moisture content, pasta behaves like a glassy polymer. The glass transition temperature of dry starch is approximately 240 degrees Celsius. Below this temperature, molecular motion is severely restricted. The glass transition temperature, Tg, is approximately 240 degrees Celsius for dry starch. But here's the critical insight. Water acts as a plasticizer, dramatically lowering the glass transition temperature. This is why pasta cooking occurs at 100 degrees Celsius, rather than requiring much higher temperatures. For fully hydrated starch, the glass transition temperature drops to approximately 60 to 80 degrees Celsius, well below the boiling point of water. Let's examine the cooking process, stage by stage. In the first 3 minutes, water begins penetrating the pasta surface. The diffusion of water into a solid follows Fick's second law. The rate of change of concentration with respect to time equals the diffusion coefficient d times the second spatial derivative of concentration. So what is the diffusion coefficient for water diffusing into pasta? Let's estimate this. For water in a starch matrix at 100 degrees Celsius, the diffusion coefficient is approximately 10 to the negative 10 square meters per second. We can estimate the time required for water to penetrate a distance L using the diffusion timescale formula. Time is approximately equal to L squared divided by D. Consider a typical spaghetti strand with diameter 2 millimeters, so the penetration distance to the center is 1 millimeter or 10 to the negative 3 meters. Plugging in, we get time approximately 10 to the negative 6 divided by 10 to the negative 10, which equals 10 to the 4 seconds. That's approximately 2.8 hours for complete hydration by diffusion alone. But pasta cooks in only 8 to 12 minutes. So what's actually happening? The answer is that starch gelatinization accelerates the process dramatically. Between 3 and 7 minutes, we reach the critical stage, starch gelatinization. This is a phase transition where the crystalline structure of starch granules breaks down. Before gelatinization, starch has an ordered crystalline structure with parallel chains. After gelatinization, the structure becomes amorphous and disordered. This transition occurs between 60 and 70 degrees Celsius for wheat starch. Gelatinization of wheat starch begins at approximately 58 degrees Celsius and completes around 64 degrees Celsius. This is well below the boiling point, so it happens quickly once pasta enters boiling water. The gelatinization start temperature is approximately 58 degrees Celsius. The gelatinization end temperature is approximately 64 degrees Celsius. What exactly happens during gelatinization? 3 key processes occur simultaneously. First, the crystalline regions of starch melt and become disordered. Hydrogen bonds between starch chains break. Second, starch granules swell dramatically, absorbing water and expanding up to 30 times their original volume. Third, amylose molecules leach out of the granules and form a gel network in the continuous phase. Let's calculate the energy required. The enthalpy of gelatinization for wheat starch is approximately 12 to 15 joules per gram. The enthalpy of gelatinization is approximately 13 joules per gram. For a typical 100-gram serving of pasta, which contains about 75 grams of starch, we can calculate the total energy. The energy required is 75 grams times 13 joules per gram, which equals 975 joules. To put this in perspective, let's compare this to heating water. Heating 1 liter of water by 1 degree Celsius requires 1,000 grams times 4.18 joules per gram per degree times 1 degree. That's 4,180 joules. So gelatinization requires only about 23% of the energy needed to heat 1 liter of water by 1 degree. The process is energetically favorable. Now we reach the critical dente window, typically between 7 and 9 minutes for standard spaghetti. This is where the magic happens. What defines al dente from a mechanical perspective? It's characterized by a specific stress-strain response under compression. Let me show you a stress-strain curve. The vertical axis is stress in kilopascals. The horizontal axis is strain or deformation. Al dente pasta exhibits elastic behavior with a distinct yield point. Initially, stress increases linearly with strain, following Hooke's law. Stress equals the elastic modulus E times strain epsilon. For al dente pasta, the elastic modulus is approximately 50 to 100 kilopascals. This gives it that characteristic firm but yielding texture. E al dente is approximately 50 to 100 kilopascals. At this stage, the pasta has a unique microstructure. The outer layers are fully gelatinized and hydrated, while the inner core retains some crystalline structure and lower water content. Here's a cross-section of al dente pasta. The outer layer is fully hydrated and soft. The middle layer is partially hydrated with some elasticity. The core has lower water content and provides structural integrity. This gradient is crucial. At the al dente stage, the overall water content has increased from about 12% in dry pasta to approximately 60 to 65%. Water percentage at al dente is approximately 62%. But crucially, the core still contains only 40 to 45% water. This incomplete hydration provides the firmness. Now we reach the phenomenon we're really investigating, the rapid transition to mushiness that occurs between 9 and 11 minutes. Why is this transition so sharp? The answer involves a concept from physics called the percolation threshold. When water penetrates beyond a critical volume fraction, the mechanical properties change discontinuously. The critical volume fraction, Phi for starch networks, is approximately 0.68 to 0.72. Below this threshold, there's a continuous network of starch that provides mechanical strength. Above it, the network fragments and loses structural integrity. Above the threshold, the network fragments into isolated clusters. The pasta loses its ability to maintain shape under stress. Below the percolation threshold, we have a connected network shown by these linked lines. Above the threshold, we have fragmented isolated clusters. This transition is sharp and explains the rapid change from al dente to mushy. How quickly does this transition occur? Let's calculate the diffusion time for the final water penetration. By 9 minutes, most of the pasta is hydrated. The remaining core with insufficient water is only about 0.3 millimeters in radius. The diffusion time for this final stage is 3 times 10 to the negative 4 squared divided by 10 to the negative 10, which equals 900 seconds. That's approximately 15 minutes, but remember, this is diffusion only. The actual cooking is faster because gelatinized starch has increased permeability. As starch gelatinizes, the effective diffusion coefficient increases by a factor of 2 to 3. The effective diffusion coefficient is approximately 2 to 3 times the initial value. This reduces the time for the final hydration stage to 5 to 8 minutes, consistent with the observed cooking window. Let's examine the quantitative changes in mechanical properties. The elastic modulus drops dramatically as pasta overcooks. For mushy overcooked pasta, the elastic modulus drops to approximately 5 to 10 kilopascals. That's a tenfold decrease in stiffness compared to al dente. This is why the texture change is so dramatic and noticeable. The ratio of al dente to mushy elastic modulus is approximately 10. In compression tests, al dente pasta shows a peak force around 5 to 8 newtons before yielding. Mushy pasta yields at only 0.5 to 1 newton. Why does stiffness drop so dramatically? It comes down to the rubber elasticity of fully hydrated polymer networks. The elastic modulus is proportional to kT divided by xi cubed, where xi is the mesh size of the network. As water content increases, the mesh size of the polymer network increases. Since modulus scales with the inverse cube of mesh size, small increases in mesh size cause large decreases in stiffness. Let me give you an analogy. Think of pasta like a sponge. A dry sponge is rigid and brittle. A slightly damp sponge is flexible and elastic. This is like al dente. A fully saturated sponge is soft and collapses easily. This is like overcooked pasta. The sponge analogy. A dry sponge is rigid. Add some water and it becomes elastic and flexible. Add too much water and it becomes soft and collapses. The same physics governs pasta. Temperature also plays a crucial role. At higher temperatures, polymer chains have more thermal energy and can move more freely. From a thermodynamic perspective, the transition involves a massive increase in entropy. Ordered crystalline starch has low entropy. Disordered gelatinized starch has high entropy. The entropy change of gelatinization is positive. The Gibbs free energy determines whether gelatinization occurs spontaneously. Delta G equals delta H minus T delta S. At high temperatures, the entropy term T delta S dominates, making delta G negative and the process spontaneous. The molecular weight and chain length of starch polymers also affect the transition. Amylose is a linear polymer with molecular weight 10 to the 5 to 10 to the 6 daltons. Amylopectin is branched with molecular weight 10 to the 7 to 10 to the 8 daltons. The molecular weight of amylose is approximately 10 to the 5 to 10 to the 6 daltons. The molecular weight of amylopectin is approximately 10 to the 7 to 10 to the 8 daltons. The concentration of polymer chains in the gel determines the mechanical properties through the cross-link density. The cross-link density equals mass density times Avogadro's number divided by molecular weight. Higher molecular weight means fewer chain ends and a stronger gel network. This is why pasta made from high-protein flour tends to hold its structure better. An interesting side note, adding salt to the cooking water affects the transition. Salt increases the gelatinization temperature slightly. Salt raises the gelatinization temperature by approximately 2 to 3 degrees Celsius. This slightly extends the al dente window, giving you more control. Salt also affects water activity and osmotic pressure. So how do we use this knowledge practically? The key is understanding that the transition occurs over a narrow window. For standard spaghetti cooked at 100 degrees Celsius, the al dente window is typically between 8 and 10 minutes. The transition from al dente to mushy occurs over just 1 to 2 minutes. This is why timing is so critical. Here's a graph showing elastic modulus versus cooking time. Notice the sharp drop around 9 to 10 minutes. The green region is the narrow al dente window where the texture is optimal. The traditional bite test is actually a compression test. When you bite pasta, you're applying stress and measuring the resistance and texture. Al dente should show initial resistance, then yield with a slight snap. Mushy pasta compresses easily with no resistance. An advanced topic. What happens when cooked pasta cools? This process is called retrogradation. Starch chains partially recrystallize, forming new ordered structures. This is why leftover pasta stored in a refrigerator becomes firm again. The starch undergoes retrogradation and forms resistant starch. Retrogradation is most rapid at temperatures between 4 and 10 degrees Celsius. This is actually beneficial from a health perspective, as resistant starch has prebiotic properties and lowers the glycemic index. How does pasta compare to other starchy foods? Rice, potatoes, and bread all undergo similar transitions, but with different timescales and temperatures. Rice starch gelatinizes at 68 to 78 degrees Celsius, slightly higher than wheat. Potato starch gelatinizes at 55 to 65 degrees Celsius, lower than wheat. Each starch source has different ratios of amylose to amylopectin, which affects texture. High amylose content gives firmer texture. Let me summarize why the al dente to mushy transition is so rapid. 3 factors combine to create a sharp transition. First, the percolation threshold causes abrupt network fragmentation when water content exceeds the critical value. Second, accelerating diffusion, because gelatinized starch becomes increasingly permeable to water. Third, nonlinear elasticity. The modulus scales with the inverse cube of mesh size, so small changes in hydration cause large changes in stiffness. These three factors, percolation threshold, accelerating diffusion, and nonlinear elasticity, combine to create the sharp transition from al dente to mushy that we observe. Let me give you a quantitative summary of the key parameters we've discussed. Diffusion coefficient, approximately 10 to the negative 10 square meters per second. Gelatinization temperature, 58 to 64 degrees Celsius. Al dente elastic modulus, 50 to 100 kilopascals. Mushy elastic modulus, 5 to 10 kilopascals. Percolation threshold, 0.68 to 0.72. In conclusion, the rapid transition of pasta from al dente to mushy is a beautiful example of materials science in action. It involves phase transitions, polymer physics, diffusion, percolation theory, and mechanical properties. This transition is not gradual, but catastrophic, occurring over just 1 to 2 minutes due to the percolation threshold and nonlinear scaling of mechanical properties. Understanding the underlying science not only satisfies our curiosity, but also helps us cook better pasta by appreciating the narrow window of perfection. The same principles apply to many other foods and materials. Whenever you're dealing with hydration of biopolymers, you'll see similar physics at work. This raises interesting questions for further study. How do different flour proteins affect the transition? What role do lipids play? Can we engineer pasta with a wider al dente window? Thank you for joining me on this rigorous scientific journey into the physics of pasta. The next time you cook spaghetti, remember you're witnessing a complex interplay of thermodynamics, polymer physics, and material science.